Good day! In this video, we are going to discuss about decidability. I am Clent, Japhet, Poledo, and I'll be firstly introducing the topic. In decidability, there are three questions that needs to be answered. First is how can we tell if two regular expressions define the same language? Next is how can we tell if two FAs are equivalent? Lastly is how can we tell if the language defined by an FA has finitely many or infinitely many words in it? So in mathematical logic, we say that a problem is effectively solvable if there is an algorithm that provides the answer in a finite number of steps, no matter what the particular inputs are. A good example for this is the quadratic formula. Using that formula, we can get the roots of any quadratic equation, no matter what the inputs are. Also, the number of steps that we have to do is always finite. So there are two concepts in this lecture, and first is the decision procedure. So it is an effective solution to a problem that has a yes or no answer. Next is decidable, in which it stands for a problem that has a decision procedure. So let's look at this problem. Determine if two REs define the exact same language. In the past, what we use is our intuition. So our approach for this is to just see if they are the same language by looking at it and trying to infer what these languages are. So using our intuition, we can just see that the first one, or the one at the left side, always starts with A, and the one on the right side always starts with B. Then they are not the same language. So this example is very easy. Next is this. It's slightly more complex, but after some investigation, we can see that these define the language of the words that are even in length. So these REs define the exact same language. Lastly is this. The left side is difficult to generalize, and the right side is somewhat easier, so it's just either the null string or something that starts with A or something that has AA within the string. So after some investigation, these two are actually the exact same language. But it is very difficult. What if we can't recognize what language each RE defines? So one approach is to generate many examples. So we can just brute force our way by checking if both have lambda, both have A, B, AA, AB, so on and so forth. So this is a problem. What if there is no difference after a lot of tries? Can we say that the REs are equivalent? Also, what if the smallest difference is at 2 million letters? So this is not the solution we are looking for. We need to find a solution that we can solve the problem in a finite number of steps. Good thing, there is a way to do that. For us to get the equality of two language, we have this. So this is mainly for FA, but with Clent's theorem, every FA has an equivalent RE, and every RE has an equivalent FA. So with that, this can also be used for both FA and RE. So given languages L1 and L2, we can construct FA that accepts the language, the intersection of L1 and the complement of L2, plus the intersection of L2 and the complement of L1. So the one in the left side is all words that are in L1 but not in L2, and in the right side is all words in L2 but not in L1. So for the language to be exactly the same one, this machine should not be able to accept any words, even lambda. So let us visualize this. So if we try to draw the sets, so firstly we have the L1 intersect with the complement of L2, and this must not have intersection for the strings to be the same. So to visualize this, let's say this is the universal set, and let's try to first visualize the complement of L2. So let's say if L2 is this, the one on the outside, then for there to be no intersection between L1 and L2, or the complement of L2, then it must be somewhere here, the L1. And this is the complement of L2. in the right side, we have all words in L2 but not in L1. So let's draw the universal set, and then let's try to draw the complement of L1. Now, for there to be no intersection, L2 must be somewhere in here. So let's label this L2, and this is the complement of L1. So we can see here that L2 is actually a subset of L1. So we can write L2 is a subset of L1. And also, in here, you can see that L1 is a subset of L2. Now, for this to make sense, then L1 must be equal to L2. So that is what is meant by this FA. So we already know the concepts behind that FA. So we know L1 and L2 since they are just given, the complement of L1 and the complement of L2 as it was tackled in the past lessons, and now we just need to know how to know if FA accepts any words. So the first method is just to convert the FA into a regular expression since every regular expression defines some words. A proof of this is by using an algorithm. So first is we delete all stars, and then for each plus, throw away the right half and the plus sign itself, and when there is no more star and plus, we remove the parentheses and concatenate the remainders. So let's do an example. So now if we try to do lambda plus a, and let's say ab star plus ba star. So let's try to see if this generates at least one string. So using that procedure, firstly we must remove all stars. So we'll be left with lambda plus a, then ab plus ba. The next is to remove the plus sign and the one in the right. So this will just become lambda, and this will just become ab. And then just remove the parentheses and concatenate, we'll be left with ab. So it generated at least a string. So this is true for any RE. So even the smallest RE, so A is an RE, and using the procedure, we get at least one string, which is A. Now the question is, if all RE accept at least one word, then should all FAs also accept at least one word? The answer to that is no, because we can convert FA to RE if the FA does not have a path from start state to final state. So these are the cases when that happens. First is when there is no path between the start state to the final state. The next case is when there is no final state at all. And then the last case is when there is a disconnect between the start state and the final state. So this leads to the next method.
Hello, I am Irene Jane Sabulao, and I will be continuing the presentation with Method 2, which is another approach to determine if a machine accepts any words. Method 2 involves examining the finite automaton to see if there is a path from the initial state to an accepting state. If such a path exists, then the machine must accept some words. Here's how Method 2 works. First, paint the start state blue. Next, from every blue state, follow each edge that leads out of it and paint the connecting state blue. Then delete this edge from the machine. Then, repeat step 2 until no new state is painted blue, and then stop. Finally, when the procedure has stopped, if any of the final states are painted blue, then the machine accepts some words. If none of the final states are blue, then the machine does not accept any words. Let's illustrate method 2 with an example to see how it works in practice. First, paint the start state blue. Then, trace the edge from the blue state and paint the connecting states blue. Then, delete the edge from the machine. Then, repeat the steps until we can't paint any more blue states. In this example, since none of the final states are blue, this means that this machine does not accept any words. As we've observed in this example, when we apply method 2, we notice that step 2 cannot be repeated more times than there are total states in the machine. In other words, if a machine has an n number of states, then after n iterations, it's either all the states are colored blue or the procedure stops. Based on our observation from the example and the iterative nature of method 2, we can summarize it as a theorem. Let f be an FA with n states. Then, if f accepts any words at all, it accepts some word with n or fewer letters. This theorem provides a clear and concise summary of the behavior of method 2 and its relationship to the number of states in the machine. Now, let's delve into the proof of Theorem 15, which sheds light on the connection between the number of states and the length of accepted words. To prove Theorem 15, we need to understand the significance of the shortest path from the start state to the end state in an FA. If this path does not contain a circuit, it means that the machine can visit each state at most one time. In this example, the path from the start state to the final state without a circuit ensures that each state is visited at most once. Therefore, the path will have at most n edges and generate at most n letters. The proof reveals that the shortest word recognized by an FA must have at most n-1 letters, where n represents the number of states in the machine. This insight is crucial in understanding the relationship between the number of states and the length of accepted words. Let's explore method 3, which provides another approach into decidability based on the shortest word length. Method 3 involves testing all words with fewer than n letters to determine if the finite automaton accepts any of them. If the machine accepts none of these words, then it accepts no words at all. The proof we discussed earlier demonstrates that the shortest word recognized by an FA must have at most n-1 letters. Applying method 3, if an FA with n states accepts any words, it will accept some word with n or fewer letters. Let's explore an example to determine if two regular expressions are equivalent. Consider the regular expressions R1 and R2. We need to determine if the languages represented by these regular expressions are the same. So, let R1 be FA1 and R2 be FA2. Then, the machines for FA1, FA2, and their complements are illustrated here. We have labeled the states with the letters P, Q, R, and S for clarity. Then, instead of using the logical formula, we build our machine based on the equivalent set theory formula. By solving the first half of this formula, we can illustrate the first half of the machine as this. Then, by solving for the second half of the machine, we can illustrate it as this. None of the states in these two machines are marked with a plus, which means neither machine has any final states. If we added these two machines together, we would get a machine with 9 states and no final state. Since it has no final state, it accepts no words, and the two languages FA1 and FA2 are equivalent. This ends the decision procedure. There are no words in one language that are not in the other, so the two regular expressions define the same language and are equivalent.
Now let us proceed into defining what the Theorem 16 is all about. This theorem states that, first, there is an effective procedure to decide whether a given FA accepts any words. 2. There is an effective procedure to decide whether two FAs are equivalent. And 3. There is an effective procedure to decide whether two regular expressions are equivalent. All of these are actually a summary of what my groupmates discussed in the previous slides about how to determine whether an FA accepts any language or not. Now, let us learn how to determine if a language is finite or infinite. Doing this for regular expressions is very easy. All you have to do is to check if the symbol star or clean star exists. If it does, then it is infinite, and if not, then it is finite. One exception to this, however, is if lambda is followed by a clean star. Since lambda is considered null, then it can't be infinite. Let's try answering this example. Which of the two is infinite and why? So this is the first RE and this is the second RE. The answer for this is that the second RE is the one that is infinite, because as you can see, the clean star is outside the parenthesized expressions, unlike the first one, which is, as you can see for this parentheses, it is inside. Very easy, right? Now let's proceed to determining if a finite automata is infinite or finite. The most common or easiest way to do this is by converting the given FA to RE and determine if a language defined by RE is finite or infinite. But there is another way to do this, which is what I will discuss today. This method is under the Theorem 17, which states that we should let F be an FA with n states. Then if F accepts an input string W such that its length is greater than or equal n and is less than 2n, then F accepts an infinite language. And 2, if F accepts infinitely many words, then F accepts some word W such that its length is greater than or equal to n and is less than 2n. To further explain this, let us have an example. If you remember last week's lesson, specifically on the second version of pumping lemma, it stated that if there is some word W with n or more letters, then we can break it into 3 parts, x, y, and z. And for this figure, the x is this, the y is this one, and the rest of it is the z. So It is evident in this figure that if we loop n times in y, it will create infinitely many words. Now let's try to check it with theorem 17. So let's try to satisfy theorem 17 with this from this example. Again, if you can remember, the equation that we need to satisfy in theorem 17 is that W should be greater than or equal to n and less than 2n. So for this equation, let's identify how many n's or states we have first so that we can see, we can continue proving it. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 states. So let's put 10 here. Then let's leave the length blank first. Then we will fill that in later. Mine is less than 2 times 10, which is n. So to clearly see that we will have 10 should the RW should be greater than or equal to 10 and less than 20. Now let's try generating a word from this equation or from this circuit. Let's try to hit one each state at least one. So we will go from, let's do this sequence like 1, 2, 3, 4, 2, 3, 5, 6, 7, 8, 7, 8, then 7. There. Let's try to list that. First, starting off with 1, of course, just 1, followed by 2, 3, 4, and then going back to 2, 3, 5, 6, 7, 8, 5, 6, 7, 9, and 10. So that's our W. Let's count how many states we have. The length. Let's count the length of our word. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Sorry, I miscounted. So we have 14. Let's put the length of our word here, which is 14, which, as you can see, clearly it satisfies the equation where W is greater than or equal to 10 and is less than 20. Okay, so now that we're done with theorem 17, let's move on to the final theorem that we will discuss for this chapter, which is theorem 18. Theorem 18 states that there is an effective procedure to decide whether a given FA accepts a finite or an infinite language. So a proof for this is that if the machine has n states and the alphabet has m letters, then in total there are different input strings in the range of given by this one. And then we can test them all by running them on the machine, which is this one. If any are accepted, the language is infinite. If none are accepted, then the language is finite. So let's have this example. A machine has 3 states and the alphabet has 2 letters. So the M here is the letters, the two letters, and the n is the number of states, which is 3. So let's fill that equation in, and then we will have this, which, and for this problem, we will need to test 56 number of strings. And based from what I've said, if any of those 56 strings are accepted, then the language is considered as infinite. And if none, then the language is considered as finite. Now, uh, if it is often considered that FA, converting FA to a regular expression is more efficient. However, suppose that an FA is an actual physical machine that is sitting in front of us. We may not know its exact structure inside, or it may be extremely complicated. Even though we have an effective procedure for converting it into a regular expression, we may not have the capacity or time or whatnot to do so. So, so the things that we have discussed for this lesson is more suitable for complex questions. And that ends our presentation. I hope that you have learned something from us. If you have any questions or clarifications, don't hesitate to approach us, the reporters. Again, this is Camyl, Magdalyn, Tanjay, and with my group mates, Clent, Japhet, Poledo, and Irene Jane Sabulao. Thank you so much.